Hello, everyone. Good afternoon. First of all, thanks for choosing to attend the session at 3:50. So let me get started. And I'm Guna Kambalimath, software engineer at IBM. So the topic I'm going to discuss about today is one operator to rule them all, choosing the best CRD management strategies for your applications. So here the keywords are CRD and operator. And I'm sure many of you would have either extensively worked on it, used it, or have attended a couple of sessions which have been going on since yesterday, and a couple of them were about operator. Yet, to make sure the flow of the session is right, I'm just going to give an analogy about the operator, how it works. So if you have an extensive understanding about it, so please hang in there for a couple of minutes, because it's kind of important to capture the flow right. So let me just get started with an analogy. So you all know that Kubernetes provides its own resources, which are a deployment, stateful set, etc., for our benefit. And you also know a basic of how it works. So when you create a deployment, you're basically stating the desired state of your system, where saying that I want this application, these many replicas, and this is the resource limit, etc., etc. And when the state of the system isn't abiding by that, so there is something in the system that is making sure that it is. Now, so here is, yeah. So here, let's say this is your deployment, and these are the pods. These are the pods that got created because of your deployment. So when you delete a pod, or when you're trying to update the pod, which is basically the child resource of your deployment, right? It makes sure there is something that makes sure, which is in the, like let's say replicas. You want 2 replicas, there has to be 2 replicas if you try deleting it, or maybe if you try updating the image, resource limit, etc. Whatever you have specified in your deployment gets updated back to your pod. Okay, that is ensuring the desired system. So who ensures that? It is your Kubernetes has a concept of controller. So what does a controller do? It ensures the desired system, desired state of your system. So your deployment is a way of specifying the desired state, and your deployment controller watches on that desired state, which is your deployment, and let's say there is a create or update event. It makes a check. Like, for example, are there n replicas? Is the resource limit right? If it is right, it does nothing. Else, it will go ahead and create that, or maybe update the pod accordingly. If there is an update event saying that you have updated the image, your controller is the one which holds the logic, which will go and check the desired state. If the image isn't right for the existing pods in your cluster, it will go ahead and update. Now, this is what Kubernetes is providing to you. It is watching 2 things over here, your deployment resource and your child resource that got created as a part of it. Now, this might not be necessarily sufficient always, right? You might want your own kind of resource, your own controller, which is ensuring some kind of desired state in the system. So Kubernetes provides a way for you to develop your own custom resource, develop your own controller on top of that. So I have taken a very simple example, just with the idea that we shouldn't get swayed away with the examples. It's more about understanding the concept. So here, let's say I have an example where I have a cluster, and each namespace is dedicated to a different team. Now we want a rule saying that, you know what, for any front-end deployment that gets deployed in any namespace of the cluster, the CPU and resource usage shouldn't exceed a certain limit. Now, I as a developer, let's say I try to create a deployment with 300 megabytes and some like 100 millicores. But there has to be something running in the cluster that doesn't let me do that. It goes and updates it back to some maximum limit that the admin has defined, for example. So here, I have defined some custom resource definition. This is something that Kubernetes lets you do. So here I have 2 parameters under the spec, CPU limit and memory limit. Remember, the keyword here is custom, because it's something that we are defining, right? So except for the fact that your custom resource definition has to abide by certain rules, which is nothing but it needs to have an API version, kind, metadata, just like any other resource for Kubernetes. Except the entire section under spec is totally under the developer's control. So in this example, I have 2 things, CPU limit, memory limit. This is my desired state, saying, you know what, when I give the CPU limit and memory limit, and I create this custom resource, something like this, there has to be a controller which makes sure no matter what front-end deployment, the CPU and memory limit has to be within this range. So that's the use case, a very simple use case. So your custom resource controller is watching on this resource. It receives some event, and it will just make sure any front-end deployment, is it really abiding by that? If it is yes, do nothing else, go ahead and update the respective deployment accordingly. Now, let's say somewhere in between your deployment is up, it is abiding by the rule, whatever desired state you have mentioned. In your deployment, if someone tries to update the deployment again back, like increasing the given limit, that time your custom controller is also responsible for watching that event and updating it back to the required desired state. So this is what your custom resource controller does. And that's the basic understanding of what a CRD is, what a custom resource controller is. So therefore, what's an operator? An operator is nothing but your custom resource controller. It's a way for you to develop your custom resource controller. So given that we have a clear understanding of what this is, let's get to the internals. So what is exactly happening within your controller? So there are a few key components over here, something called as a reconciler, an informer cache, and there is a Go routine and some Go channel. There are many Go routines, but what each of them does is not in the scope of the discussion. So yeah, there is reconciler, there is informer cache, and there is Go routine, which is watching on your resources, etc. So what is happening here? Now, let's say you created a custom resource, the same one, just like what I showed in the previous slide. And it goes to that event, the create event goes to a Go channel. And then here is your reconciler. It sees, oh yeah, okay, I got an create event. And accordingly, I need to make sure that I update all the front-end deployments for that CPU and memory limit. So this is the black line here. It is one part of the flow. You got the custom resource. You're updating your front-end deployments to the desired state. There is another part of the flow where you see in the green line, basically the second thing that I talked about. After your deployment is created, if someone, while your cluster is up and running, is trying to update it to a bigger, a higher memory value, it sees, okay, it gets an event, okay, someone tried to update it. After updating, it needs to check, is it really abiding by the desired state? Like, let's say the user has updated to 300 megabytes. The value that the desired state is saying, your custom resource is saying is 250. So it has to check what is the current state that we need to check. So it goes and checks something called as an informer cache. So you might be wondering, instead of informer cache, it could have directly called the API server and gotten that resource and checked what is there within the spec. But rather than that, it uses the informer cache. Why? So that we reduce the number of calls happening to the API server, and this is reduce the latency, hence a better performance. So that is about your informer cache. It caches the resources. Now, this informer cache also keeps resyncing. Let's say your operator has missed some event, okay? In that case, it keeps resyncing from the Kubernetes API server the state of your objects. So within a controller, these are the things that are happening. Your CR is getting created, the event comes through a Go channel, which is a part of a Go routine. Your reconciler gets it, it updates to ensure the desired state. If the child resource or the other resource which it is watching, if there is an event on top of that, it makes sure is that event, whatever has happened, is it really abiding by the desired state? No? Then it goes ahead and updates it back. That's what the key components here is: the Go routine, the informer cache, and the reconciler. This is important for us to understand the next few slides. So coming to the actual topic in hand, given that we have gotten a context of how a controller works and more on that. So what's the right choice for you? One CRD per operator pod and multiple CRDs per operator pod. So to be able to visualize this, before we go to the key factors like what should be your choice, I have added a couple of diagrams over here. So one example which we are already aware about, let's call it resource constraint policy. I have added one more controller over here, which is security constraint policy. Let's add one more functionality. For any front-end deployment, I always want the security context with these values, this user and this particular group. And I want a controller which makes sure that that is what is happening. So now here you have the controllers in two different operator pods, right? Like in your Kubernetes cluster, it's completely in two different operator pods, but the components remain the same, the Go routines, the Informer cache, and the flow. And both of them are trying to update the front-end deployments itself. So that's one controller per operator pod. But when you put two controllers per operator pod over here, it's the same. You have two controllers. Both of them are more like the routines that are being spawned by your main thread. And you have just one more added thing here is your shared Informer cache. So now, what is a shared Informer cache? Let's say you have two controllers. Both of them are trying to watch the front-end deployments itself. Now, you wouldn't want two separate cache for that. It's just a redundancy and a higher memory usage. So the shared Informer cache is meant in the use case where there are multiple controllers and many of them are trying to watch the same set of resources. It could be any resource. It could be your deployments, or it could be deployments with a certain filter, like label selectors, right? So that's about having a shared Informer cache inside within two controllers per operator pod. So given that we have a visualization of what it looks like, I'll go to the next slide. So out of these two approaches, what is the right choice for you? What are the key factors that you need to consider? So it's performance and resource usage, stability and failure isolation, RBAC, independent life cycle, and teams. So I'll just go through them one by one. First thing is your memory usage. So now if you choose one controller per operator, and considering cache size as one of the factors, there will be a redundancy in cache if there are multiple controllers trying to watch. If you have two controllers and two different pods, but both of them are trying to watch the same set of resources, and you can actually put them into the same operator pod, but yet you choose to put them into separate operator pods, that time there will be a redundancy in cache, meaning a higher memory usage. And if you put them into the same operator pod and there is a shared Informer cache. Distribution of resource usage. Now, what can act as a con for you that can be a pro, like I mean an advantage when you consider distribution of resource usage. So if you have, if you put all the controllers together in one pod and there is a very big workload because your operator, the cache rate, it tries to cache all the resources that it is watching. So the cache size might get bigger if you create like thousands of CRs or many other deployments that it is trying to watch. So there are chances that it could go to OM state, and there have been scenarios and issues, open source issues, that made it go to the out of memory state. So that's the con when you put a high workload with multiple controllers per pod. But if it is obviously in different pods, there is a better resource, there is a better resource distribution. So two key points that we need to know here is shared Informer cache comes into picture only when there are multiple controllers are watching the same kind of resource. But if they're watching different kinds of resource, it doesn't really matter. They are using different caches, okay? And always watch, whether it's a single controller or multiple controllers per pod, always watch only the required resources. If you want to watch only front-end deployments, there is a way where you can add the label selector, a filter that you want to watch only these. Because if you say, I want to watch deployments, like it's a bug in your code, I want to watch config maps, etc., that time it will cache all the config maps and all the deployments unless you have specified a label selector, else your cache size is going to increase and the pod will go to OM state. That's about memory usage. Coming to performance, so before I talk about the statistics of performance, etc. So another thing that you saw in the diagram is the number of Go routines. So for that, I have some statistics. Here, yeah, these are two different use cases. There is your reconciler function. You have your custom resources. Now, let's say you create one custom resource per namespace or any number of custom resources. It depends upon your application logic, right? So consider deployment, for example. if you create your first deployment and the pods are getting created, how frustrating it would be when you create your second deployment and it has to wait for the first deployment to be over. That doesn't look good. That's not a good design. So if by default, when you're developing an operator, the logic is that the value here, the max reconciles 1, which basically says I have one go routine, one channel, and whatever resources that you are creating, they are going to be processed sequentially. Meaning the first CR will get created and all the processing will happen, and then only your CR2, the second resource, will be considered. So it completely depends upon your use case. If you're okay with the fact that they can be processed sequentially in the cluster, you can keep the max reconciles to 1. But if you want parallel reconciliations, that time, when we set a higher value, each of them can be processed parallelly. Now, it's a different use case when you have max reconciles 10 and you create like 20 resources or 100 resources at a time. Obviously, they will be processed. They will kind of be put in the queue, put in the channel, different ways, and some of them will be processed sequentially. But the parallelism on a whole will increase. So one thing you have to know here is that the number of go routines increases with the number of max reconciles value. So for that, I just did a few experiments and have just some basic statistics with simple examples. So here, first thing is the number of go routine, what is the number of go routines proportional to inside an operator? So here, the x-axis is number of custom resources, and here is the number of go routines. So you can see that each line, they represent more like one CRD or one controller per operator. The next one is 2, and the next one is 3 controllers per operator. So when I spin up my operator with just one controller, so you see that the starting point is, there will be 30 go routines. And if I had 2 controllers inside an operator pod, it's going to be 45 and 60. So with each controller that you're trying to add to the operator logic, more is the number of go routines. I know the increase here is 15. Why? That's again, there's a lot going on in the operator logic, but the key takeaway from here is that with the increase in the CRDs, the number of go routines also increases. There's one more thing to observe. The custom resources, as soon as you create your first custom resource, you see that there is a spike in the number of go routines. Okay, it's a value of 8. Okay, but then when the count increases, no matter how many custom resources you create, the number of go routines is remaining constant. Why is that the case? Because it's not like with every CR you create a new go routine is going to get spawned, right? It shouldn't be like that. So because it gets queued up in a Go channel, hence it remains constant. So it doesn't depend on number of custom resources you create. It depends on number of controllers or CRDs you are trying to inculcate within one operator pod. Going to the next slide, which pretty much sums up what I said until now. Your number of go routines is directly proportional to the number of reconciles. How much do you want to be processed? Do you want what kind of parallel processing you want for your resources? And it depends upon number of CRDs. Now, given that we understood this, I came up with a basic formula on some experiments that I did. How can we estimate the number of go routines? Now, before I say this, many of you might be wondering that go routine is a lightweight thread. Should we really bother even if there are like 1,000 go routines, etc.? So I'm not sure how many of you are aware. There are designs or there are clusters where you have a central control plane cluster and many worker node clusters where we can actually have an operator in the control plane cluster which is trying to watch on the resources on other worker node clusters as well. So in such cases and under a higher workload or even watching not just your custom resource or some other KTS resource like deployments, config maps, etc. In such cases, it could significantly increase and could lead to CPU throttling. It's not a case that happens in a single cluster. It's more like a higher workload and a different architecture all in itself. So given that that is clear, here I have this formula. I won't be explaining each and every parameter of this. So based on this formula, or let me just put it briefly, your operator itself, when you spin it up, there will be like 15 go routines. And with every CRD, I see that there were yeah, there were again another 14 Go routines, and depending on your reconciles as well, per CRD it increases. Also, what are the number of resource types you're trying to watch? So the more the resource types you're trying to watch, deployment, stateful set, etc., as a part of your controller itself, again, there is going to be a increase in the number of Go routines. So applying this formula, I just saw what is the statistics when we have one controller per operator. So you see that the value is 640, and here you see that the value is 585. So clearly, when you have multiple controllers per operator, the number of Go routines is less. But again, just like memory usage, distribution of resource usage. Like if you have it in multiple pods, the CPU usage will be spread across pods and nodes. And when you have it in a single pod, it can lead to higher workload and CPU throttling. And that's about performance and CPU usage. Coming to the next part of the discussion, stability and failure isolation. Now here I've taken a simple example. Let's say you have two controllers within an operator pod, and you try to, one of them has a bug, a critical bug. So you create your resource or maybe update your resource. So your controller A crashes, okay? So that time it can take down your whole operator pod, and when you create a custom resource of kind B, which is for a different controller, it won't be able to respond. It goes unhandled. So that is one of the factors that needs to be considered. The first point over here, failure isolation, it talks about the same. One thing we should always make sure when we are trying to integrate two controllers is that mindful development and a good amount of rigorous testing. The second thing is checking existence of dependent resource. Now, let's say here I have a simple example, which is open source. Okay, let me just, all right. I'm sorry. Okay, I'll just, now let's say you have a resource which is a DB and a DB backup. Both of them are different resources, and you're trying to integrate that within one operator. Now, you don't need a DB backup unless there is a DB, right? So your DB backup, when you try to create a DB backup resource, it should have a check. Is the DB really existing? So PostgreSQL does the same thing in their code, in their check. They have they have a DB and DB backup, two different resources. And before a DB backup gets created, it makes sure there is a DB instance as well. So when you integrate multiple controllers, this check is this dependency check is quite simplified. But you have it in different different operator pods, meaning different logic all in itself. So that time the check can get very tedious. You will have to look into unstructured data, like you have an unstructured list in Kubernetes while you're trying to develop it in Golang and unmarshal it. And until now, I haven't been able to achieve it as such, but yeah, that can get tedious. So that's one of the disadvantage for having one controller in that, and it's advantage of having multiple controllers, unless if they are dependent, if the two resources that you're trying to put together are dependent. That's about stability and failure isolation. Coming to RBAC. So here I have an example. Any of you who doesn't know about Prometheus and Alert Manager, to put it in brief, Prometheus is something that just monitors your metrics on your cluster, which is pod and node, etc., and stores it in the DB. And Alert Manager is the one that routes the alert to you on your emails, like etc. Like if there is something uncertain going on in the cluster. So, like your node is down or the memory usage has exceeded a certain limit. So here, let's say we try to deploy both of these using an operator. So your Prometheus would need permissions to be able to watch the pods, list the pods, etc. But your Alert Manager should be able to access the secrets. Now, if both of them are getting deployed from a same monitoring operator pod, so here, what happens is your cluster, your operator's cluster role, which is trying to create it, it in itself needs to have the permission to be able to watch the pods, watch the secrets, etc. So it's more like if I'm in a cloud account and I want to give certain privileges to my colleague, it's necessary that I myself have those privileges. Your operator works just like that. So here, again, just to add, that I know there is a Prometheus operator open source. This is more of an example to give you, give you an example using the key factor RBAC. All right, now your operator has the permissions to list the pods, list the secrets, etc. Now, you can't, it's not ideal to bind them to the same service account, right? That means your operator pod should be able to create and watch your service accounts as well, if it has to give the, create different service account and bind your cluster roles to that. So what happens here is that you're just leveraging, giving too much access, which kind of goes against the least privileged access in Kubernetes. There is one more point to prove why that is the case. Okay. So the first point here pretty much sums up what I was talking about. With one controller per operator, you will have isolated RBAC policies, like each of your, it's because it's completely different code, completely different operators. It will have, one of them will have just to be, just the permission to watch secrets, the other one for pods. But if you integrate them together, you're giving overprivileged access. In such case, what could be a workaround? You could just leverage the responsibility to the user who's trying to install it. You know what? You create the cluster resource, you create the service account, and then install the custom resource you want. And there is a Prometheus platform guide that actually mentions that, which actually leverages that to, it is from the Prometheus operator itself. It leverages that responsibility to the user. So one key point that you need to consider here is, even if a controller is configured to watch only specific instances of a resource type. Now, let's say I have like n number of secrets in my cluster, but I want to watch only 2 of them. Even if you modify your controller logic, putting a filter saying that you watch only this, but you will still need to give the RBAC to be able to watch all the secrets. Else, when you boot your controller, it doesn't work. It says, I do not have the permissions to be able to watch all the secrets. Because although whatever it is going to cache, it is going to be just the required secrets, but when it is watching, it is going to watch all of them. So that's one key point that we need to consider. Also, make sure you give the permission just to be able to watch within a particular namespace. So that's about RBAC and having some RBAC isolation and the pros and cons. Coming to independent lifecycle and teams. So here, this is kind of a situation that I had faced. So I'm just explaining with an example. You have some app deploy controller, app backup controller, but this is being owned by 2 different teams. Now, let's say the image that it is deploying is being owned by 2 different teams. So, and your team A has to do a release on August 30th for some critical bug, but your another team is going for a new feature support, which is kind of a closer date for your first controller over here. So each of them own 2 different components. Now, here, what's the choice? Since the dates are quite closer, either you have to combine the releases into one flow, which will kind of, compel them to rush towards the date, or they'll have to go ahead with separate release processes in quick succession, which is operationally redundant. So when you're doing this tight, it will basically lead to a tight coupling of your releases and a lot of coordination requirement between the teams. So that's one of the cons that we go through. But unless you think that it is manageable, the release process is quite in place to be to handle this, or it's the same team which owns both of them, sure, it acts as it shouldn't be a disadvantage. So that's about independent lifecycle and teams. Now, here are some set of references that I went through. This is basically some issues which talk about performance and resource usage, and some QBuilder dogs and certain blogs. So please go through the same to understand all these factors a little better. Given that, so I've explained all this, and hence these key considerations, which you need to consider. On top of that, I just want to add a couple of things. It depends on your complete performance, or what is the way you want to go with one controller or multiple controllers per pod. It depends on other factors like your controller logic, your CPU and infrastructure, a good amount of functionality testing and performance testing as well. So these are some things we shouldn't skip while we are choosing what's the right way to go with. And is it really necessary to couple your controllers or put your controllers together? Are they really so much dependent on each other? So that's what matters. And yep, that's it. Going to Q&A if anyone of you have any questions. Questions? That's all right, you can.
Hello.
Sorry.
If my controller creates a deployment and if I manually update the deployment, so will the Kube server will do the update for the deployment, or will it says this is controlled by the controller, so it will stop at that time?
If your controller, okay, if your controller is creating the deployment,
Yeah.
right?
And once the deployment is created, I updated it manually, like maybe kubectl edit or something, and then the API server will update the deployment.
No, see, if your controller has created the deployment and you edited the deployment, kubeAPI server is not going to come there and do anything on top of that. Like, I mean, it makes sure it is getting edited, right? So basically, kubeAPI server, your controller gets an update event only if your controller is actually watching on that deployment. It can just create. But if you want that event to be handled, there is a watches function within the reconciler. If you check the controller runtime or those packages, there is a watches function where you specify you have to watch this resource. If you do that, then your controller gets an update event saying that someone updated the deployment and you act accordingly. Unless you have not added that in your code, it won't get handled. It just remains updated.
But the CR, there is in CR we specify the image, right? So basically, so for example, in my CR, I have a spec section where I have added the image, and the controller will seize that and it will create a deployment. And if I manually update the image, then
if you manually
it's a race condition, right? Then what will happen at that time?
If you manually update the image in your CR and you want it to be reflected in your deployment, right?
No, if I manually update in the deployment.
Okay, if you manually update in the deployment, it will be taken care of, meaning it looks at you want your reconciler to look at the CR. What is the image? Go ahead and update the deployment. If that has to happen, you have to add the watches function with that the deployment spec, and add a filter if you want to watch setting. Unless you add it, it won't actually go ahead and check the state and update it. It's necessary to add that.
Thank you.
Yeah, that's, yeah.
Related question, right? His primary question was, is it possible to restrict editing of a deployment that's managed by a controller? So what I'm trying to say is, the deployment, if it's created by the controller, it should only be editable by the controller, and nobody should have the permission to edit that resource. Is it possible to do that?
Okay, so just like I said, if you have, like as soon as you edit, if you want an error message saying that you are not allowed to edit it, right. It's not necessarily from your controller. Like ideally you will be able to give you will be able to restrict like namespaces to certain users, right, in Kubernetes. You can either do it that way, but within your controller, I don't think there is anything that will actually stop your...
It's not within the controller, it's within the Kubernetes system itself, where you're setting up RBAC policies such that if the field says managed by the controller, only then you're able to edit. So it's essentially what I'm asking is it possible to configure RBAC such that only the controller has authority for the resource?
No, I don't think so that you can put it that way. You can only restrict in certain ways, like other applications that are running inside the cluster do not have the necessary RBAC. I know you are saying we have to put the RBAC on the resource itself. But putting the RBAC on the resource itself, saying this resource, you are not supposed to be updated by anyone else, just from the controller. Yeah. No, it's not like that. If you have either restricted like namespaces to certain set of users, that's one way to restrict. And one more way to restrict is not giving that kind of role to any other applications in your cluster.
Okay.
Hi. As per your experience, I mean, what is the maximum number of CRDs you reached per operator? Like, I have an operator wherein we couldn't, I mean, as per the requirement, we had to reach the maximum of 7. So, I mean, like, what is the maximum number of CRDs you have reached per operator, and what did you do to restrain it? I mean, did you face any challenges, and then you came back and, I mean, tried it in a different way so that you could distribute them?
Okay. So I myself, not up to 7 for sure. I have seen issues which have done up to 10 CRDs per operator in the links that I have put in the references. But I myself, I had put 3 CRDs per operator, which was basically to deploy different drivers, different kind of drivers within one operator. So the challenges I faced is, okay, sorry. The challenges is that okay? Sorry. The challenges I faced is that first thing is the release cycle, it was getting a little too tedious. That is one thing. And one more thing is that example that I talked about, cache size, where I actually didn't put the label selector filter and just kept it to watch all the config maps. And when the customer itself actually created a lot of config maps for that use case, the operator, although it is completely unrelated to those config maps that they created, it was going to OHM state. So that was one challenge that I faced, I can say.
Hey,
Oh,
question.
I'm sorry, the time is up. I'll be there. Please reach out to me. Thank you. Time's up, sorry. Thank you.